Electricity. It's all around us, at work, at home, and at play. Even when we're travelling, we're constantly surrounded by electrical circuits and electronics. We take electricity for granted. Our world is controlled by it, and we expect electrical systems to work. Even more so with the development of microelectronics, these systems have become extremely reliable. Systems have even been introduced that would otherwise not have been possible. But because these have become so complex and often have no moving parts, it's often difficult to understand how they work. And sometimes it's not immediately obvious that they are working. And so if things do go wrong, it's the electronics which get the blame. Ironically, it's the lack of moving parts that makes these systems so reliable. Faults that do occur are usually in the electrical part of the system and are caused by damaged wiring or loose connections. These simple faults, which can easily be cured by a few minutes' work, are often overlooked at the expense of a perfectly good piece of electronic equipment. With the increasing level of electronics in our present range of cars, it's important that you, our frontline technicians, appreciate this and are able to diagnose such a fault when it occurs. But to do this, you'll need a basic understanding of electricity and how it behaves in automotive electrical circuits. You'll need to know how to take electrical measurements, what these measurements mean, and how they can be used to locate circuit faults. And you must be familiar with the components you'll come across. For example, the resistor, the capacitor, the diode, and the transistor. You'll need to know what these components are and the role they play in the circuits they're part of. Finally, you must understand the role of the microprocessor-based electronic control units, which are now commonplace in our cars. Although internally these units are very complicated, the way in which they are wired into the car's electrical system is quite straightforward. With a basic understanding of automotive electrics and electronics, troubleshooting and rectification work should cause you no problems. In this first section of the program, we're going to look at what electricity is and how it can be used. We all know the terms voltage and current. We also know that in the home, the electricity supply is 240 volts AC and that the supply from a car battery is 12 volts DC. But what does this mean? To understand this, you'll first need to know more about what electricity is. We can't see it, we can't hear it, we can't smell it, but we've all probably experienced its presence in what can be a painful way. There are, however, other and better ways of detecting it. But how does electricity make this lamp work? If we look at the installation, we see there's a power supply with a wire to connect it to the lamp. For convenience, there's a means of control, in this case, a switch. And finally, there's a route back to the battery. Together, these components form a circuit, an essential part of any electrical system. By making and breaking this circuit, the switch enables the lamp to be turned on and off. You probably find this quite easy to understand, but in a car, even such a simple circuit can become complicated by the difficulty in tracing the wiring. That is, if you don't know how to use a circuit diagram and you're not familiar with the symbols used. In our lamp circuit, for example, we have a battery, a wire to the lamp, a wire to the switch, and a connection from the switch to the battery negative terminal. In a car, this connection is usually made through the bodywork and the battery earth strap. For simplicity, this part of the circuit through the bodywork is not normally shown on a circuit diagram. Instead, both connections to the bodywork are represented by earth symbols. So if you see these, you can assume a connection between them. As we've seen, it's the switch that controls the circuit. When the switch is closed, the lamp is lit by the flow of electricity around the circuit, and when the switch is opened, the lamp goes out as the circuit is broken and the flow stops. It's the ability of the wires and other components of the circuit to conduct electricity which allows this flow. Conversely, it's the insulating properties of the outer covering of the wires and connectors which ensure the electricity is contained within the conductors. This type of circuit, with a single path between the components, is often referred to as a series circuit, and the components are said to be connected in series. When there's more than one path between any components, the components are said to be connected in parallel, and the alternative current paths are known as parallel circuits. It's important that you keep the idea of a circuit in mind. It will help you understand the properties we know as voltage, current and resistance, and the simple relationship between them. These properties are often explained using a mechanical model, one you should already be familiar with, an engine cooling system. You won't need to be told that whilst the engine is running, coolant is being forced by the pump through the hoses and other components of the system around the circuit and back to the pump. And if at any point the circuit branches, the flow is shared proportionally between the two routes. Just as the flow of coolant in the cooling system depends on the pump, the flow of electricity in our lamp circuit depends on the battery. Here, it's the battery which provides the pressure or voltage, and the voltage which causes the flow of electricity we know as current. The unit of voltage is the volt. Its symbol is V. The unit of current is the ampere, commonly known as amps. Its symbol is A. In some respects, electricity behaves in the same way as the coolant in a cooling system. For example, the flow of coolant is reduced by the restrictions in the hoses and other components of the system. A narrow pipe will oppose the flow more than a wide one. Similarly, the wires and other components of an electrical circuit will oppose the flow of electricity. A small diameter wire will offer more resistance than a larger one, and a long wire will offer more resistance than a shorter one. Quite naturally, this opposition to the flow of electricity is known as resistance. The unit of resistance is the ohm, and is represented by the Greek letter omega. Resistance will also depend on the material from which a conductor is made. The resistance of a conductor like copper, for example, will be very low, whereas an insulator will have a very high resistance. A loose connection or a corroded terminal will also have a high resistance. Here there are 2 points you should keep in mind. The first is that voltage, the pressure, will vary around a circuit as resistance is met. And the second is that although the flow of electricity, the current, depends on the voltage supplied by the battery, its value in amps depends on the total resistance offered by the wires and other components of the circuit. This means that in a series circuit, the current will be the same at every point, whereas in a parallel circuit, the current is shared proportionally between the various paths in the same ratio as the resistances of each path. Even so, when the paths rejoin, the current will have the same value as before the paths separated. It doesn't matter where the resistance is in a circuit. If it exists, the current throughout the circuit will be reduced. For this reason, a good clean earth connection is as important as a good clean supply connection. So to recap, voltage is the pressure in the circuit and is measured in volts. Current is the flow of electricity and is measured in amps. And resistance is the opposition to the flow of current and is measured in ohms. There's one further electrical unit you should be aware of. This is the watt. W. It's a measure of electrical power and is used to describe the power requirement of electrical equipment. For example, this lamp is rated at 21 watts. This is a feature of the bulb's design and is simply its rated voltage multiplied by the current it requires. 21 watts means that with a 12-volt supply, the bulb will draw a current of 1.75 amps. For the lamp to shine at full brightness, therefore, an essential requirement is that the circuit resistance is such that the voltage of the lamp is not less than 12 volts and that the current through the circuit is not less than 1.75 amps. It's equally important that attempts are not made to draw excessive current through a circuit. This would cause the wiring to overheat. To prevent this occurrence, protection is provided in the form of a fuse. This is a deliberate weak link in the circuit and is designed to blow before the high current damages the wiring. A fuse is also designed to protect the wiring from a short circuit. This is a fault where an insulation breakdown has provided an easier, lower resistance route for the current back to the battery. If a short circuit occurs, the fuse will blow instantaneously. Because of this protective role, it's important that when replacing a fuse, one of the specified current rating is used. If the rating is too high, in the event of a fault, the wiring would overheat before the fuse could blow. If the rating is too low, the circuit would not operate correctly as the fuse would blow under normal conditions. The final thing you'll need to know about electricity itself is the difference between direct current, DC, and alternating current, AC. Automotive electrical systems are essentially DC, that is, they operate on a current of fixed positive and negative polarity. This is because a car relies on a battery for starting and batteries can only store and supply direct current. However, the alternator, which makes the car's electricity, generates alternating current, AC, and so this has to be converted to DC before it can be used. In the home, an alternating current supply is quite acceptable as suitable electrical equipment is readily available. AC simply means the supply is continually reversing in polarity. An alternating current supply would also be acceptable in a car. That is, if we didn't rely on a battery for starting and batteries can only store and supply direct current. The conversion of AC, generated by the alternator, to DC is done using a rectifier. This is normally built into the alternator, so what actually comes out is DC. So far, we've looked at a typical electrical circuit, and we've seen that the electricity that causes it to work is described in terms of voltage, the pressure, and current, the flow, and that these depend on the battery and the resistance offered by the components of the circuit. We saw that although voltage varies around a circuit, the current is the same throughout, except as we saw earlier when parallel paths are encountered. We next saw the importance of matching the current carrying capacity of the wiring to the rating of the circuit fuse and the current requirement of the circuit load. And finally, we saw that although a car's electrical system is essentially DC, the alternator generates AC, and this has to be converted before it can be used to charge the battery and supply the vehicle's requirements. At this point in the program, stop the tape and answer the series of questions in section 1 of the accompanying workbook. When you're ready, restart the tape and resume the program. In this section, we're going to look at how electrical measurements are taken and how they're used when troubleshooting. We've already seen that it's the voltage supplied by the battery that causes current to flow through a circuit, and it's the resistance offered by the conductors and other circuit components which controls the flow. It's essential that this relationship is clear in your mind because it's this which makes troubleshooting possible. To this end, it's often necessary to measure voltage, current and resistance, and so it's important that you know how this is done and what the readings mean. One way of taking measurements is to use a multimeter. This multi-purpose meter can be switched between functions as required. It can be used as a voltmeter to measure volts, as an ammeter to measure current in amperes or amps, and as an ohm meter to measure resistance in ohms. Ohm, incidentally, was the person who deduced the relationship between voltage, current and resistance, which after him is known as Ohm's law. This simple but important rule is easily memorized using what's often referred to as the magic triangle. Ohm's law tells us that voltage is equal to current times resistance, that resistance is equal to voltage divided by current, and that current is equal to voltage divided by resistance. In this way, if we know any two values in the triangle, the third is easily calculated. Now, it's essential that you not only understand the meaning of voltage, current and resistance, but you must also have this relationship clear in your mind when taking electrical measurements. If you're not sure, stop here and think about it for a while, or even watch the first section of this program again. In practice, it's normal to troubleshoot an electrical circuit using voltage measurements, as this can be done without disconnecting or breaking the circuit under test. By measuring the voltage between the battery negative terminal and various key points around the circuit breaks or poor connections can be detected. So let's see how this is done. Assuming you've confirmed that the battery is not flat and the circuit fuse hasn't blown, you should start by setting the meter at the appropriate voltage range. With the circuit switch closed, the meter's negative or black lead should be connected to the battery negative terminal or another good earth point, and the positive or red lead connected in turn to the various connectors and components around the circuit. On the supply side of the lamp, the voltmeter should indicate battery voltage, and on the earth side of the lamp, the voltmeter should indicate no volts. A small deviation in each of these readings is acceptable. This is to allow for the normal resistance of the wires and connectors. A large deviation, however, more than about 10% of the supply voltage, indicates a fault condition. For example, a low voltage on the supply side of the lamp would indicate a high resistance, such as that associated with a poor supply connection. Conversely, a high voltage on the return side of the lamp would indicate a high resistance to earth. In either case, the high resistance will reduce the circuit current. This will be confirmed by a reduction in the lamp's brightness. To locate the cause of the fault, a visual inspection must then be made. Because voltage measurements are taken without disconnecting the circuit, the voltmeter is said to be connected in parallel. In order that the voltmeter does not affect the circuit it's connected to by providing an alternative current path, the voltmeter must have a very high internal resistance. Now let's look at how current is measured. To do this, the circuit must first be broken. And then, with the meter set to the appropriate current or ampere scale, the probes are connected to remake the circuit. Remember, red to the supply side and black to the earth side. In this case, the meter is said to be connected in series, and this means that the full circuit current flows through it. The ammeter must therefore have a very low internal resistance in order that it does not affect the normal current flow. Because current flow is the same at every point in a series circuit, the meter connection can be made wherever is most convenient. But don't forget, In a parallel circuit, the current will be split between each path. The need to break and reconnect the circuit can make troubleshooting using an ammeter a tedious job. In one instance, however, that's for checking the output from an alternator, current measurement is essential. Let's now look at the third measurement, that of resistance. This can also be a useful means of troubleshooting, but because resistance is a feature of the circuit and its components, and not of the electrical supply, the battery must first be disconnected or the circuit fuse removed. For this reason, the multimeter has its own internal battery which is connected into the circuit whenever a resistance or ohm scale is selected. The probes are connected, one at each end of the circuit or part of the circuit, under test. In the majority of cases, their polarity is not important. By systematically working around the circuit, sources of high resistance or breaks in circuit continuity can be located. One example where resistance must be measured is when a faulty ignition coil is suspected. This is because with the engine running, the coil primary circuit is being made and broken extremely rapidly by the contact breaker, and the resultant current pulses in the primary and secondary circuits are too short to be measured accurately using a voltmeter or an ammeter. The alternative is to isolate the coil from the ignition circuit and to measure the resistances of its primary and secondary windings. For comparison, the correct readings will be found in your repair manuals. If the meter readings are correct, it's unlikely that the coil is faulty. We've now looked at the three electrical measurements which can be taken when troubleshooting a circuit. We saw that voltage is measured using a voltmeter connected in parallel, that current is measured using an ammeter connected in series, and that resistance is measured using an ohmmeter, with the circuit isolated from the battery. Of these three measurements, we saw that voltage is the most convenient, as it doesn't require the circuit under test to be disconnected. At this point in the program, stop the tape and answer the series of questions in section 2 of the accompanying workbook. When you're ready, restart the tape to resume the program. In this section of the program, we're going to look at two electrical components, the resistor and the capacitor. These are used to provide more precise control over the operation of an electrical circuit. To see how they work, we're going to look at some applications you're probably already familiar with. First the resistor and then the capacitor. Resistors are devices of known resistance value and are used in a circuit to reduce voltage and thereby limit the current flow in a controlled way. They can either have a fixed resistance value, or their resistance can be variable. They rely on the fact that resistance depends on the length of a conductor and on its cross-section area. One application of a fixed-value resistor was in early ballasted ignition systems. More recently, however, the resistor has been replaced by a high-resistance wire in the harness. Nonetheless, circuit operation is identical. Here, the ballast resistance is in the coil primary circuit. By bypassing the resistance during cranking, the full supply voltage is supplied to the coil primary winding. Once the engine's running, the resistance is switched back into the circuit, thereby reducing the voltage to the coil. In this way, the engine is provided with a stronger spark when starting. Although in this case, the resistance is in the form of a wire, resistors as components are widespread in modern automotive electrical systems. One example is in the fuel pump circuit on EFI cars. This resistor is switched out of the circuit during cranking and into the circuit when the engine is running. In this respect, the circuit operates in a similar way to the ignition system we've just looked at. In most applications, however, resistors remain unseen. Perhaps the most common use of a variable value resistor or potentiometer is in a petrol gauge sender unit. Here, the circuit resistance is reduced as the float rises and increased as the float falls. This causes a corresponding change in voltage. The petrol gauge is simply a voltmeter and therefore responds to the float position. Another familiar application of the use of a variable resistance is for the dimming of the instrument panel illumination. Here, the increase in resistance as the knob is turned reduces the supply voltage at the lamp and causes a reduction in the current flow through the circuit. The result is that the panel lights dim. The second component we're going to look at in this part of the program is the capacitor. These rely on their ability to store electricity and thereby oppose voltage changes in the circuits they're part of. Some have a polarity and must be connected into a circuit the correct way round. With others, this isn't important. The unit of capacitance is the farad and is denoted by the letter F. Because 1 farad is extremely large, it's normal for the value of capacitors to be described in microfarads or picofarads. It should, however, be noted that as their electrical symbols suggest, there's not a current path through a capacitor, and so they cannot conduct electricity, although in some applications they may appear to. Capacitors are commonly used for the suppression of radio interference. They're connected between earth and the supply lead in the circuits of motors and other electrical equipment which have contacts that open and close. By absorbing the voltage fluctuations which occur when making or breaking such circuits, arcing across the brushes or contacts and the associated transmission of noise is prevented. This action is easily demonstrated by disconnecting a capacitor. Another circuit which incorporates a capacitor is the conventional contact breaker ignition system. Here, the capacitor, sometimes known as a condenser, is used in a slightly different way. Its role is to speed up the reduction in current flow through the coil primary circuit as the points open. The faster this is done, the stronger the ignition spark will be. By providing a current path of lower resistance to the gap across the opening points, the capacitor reduces the arcing and thereby speeds up the reduction in current flow. When the points close, the capacitor rapidly discharges to earth, ready for the next cycle. The effect of the capacitor is easily seen by comparing the arcing, first with the capacitor disconnected, and then with it connected. The effect of a faulty capacitor on engine performance and contact breaker life is equally evident. In this section of the program, we've seen that it's sometimes necessary to have close control over circuit operation, and we've looked at two devices which in different ways make this possible. We first saw the resistor, which is used to reduce voltage and limit the current in a circuit. We then saw the capacitor, which, although not a conductor, can store electricity and thereby absorb voltage fluctuations. At this point in the program, stop the tape and answer the series of questions in section 3 of the accompanying workbook. When you're ready, restart the tape and resume the program. In this section of the program, we're going to look at the diode and the transistor. These are two semiconductor devices which are used to control a circuit electronically. We've already seen how the resistor and the capacitor are used to control the operation of a circuit by means of their conducting and non-conducting properties. Sometimes, however, it's necessary to control a circuit in other ways. In this respect, the development of semiconductors was a major breakthrough in the world of electronics. Like all semiconductors, the diode and the transistor rely on their ability to conduct electricity only under certain conditions, hence the name. We'll see how the transistor's used later. But first, let's look at the diode. A diode has the ability to conduct electricity in one direction, but if connected into a circuit the other way round, it will prevent or block the flow. This is illustrated by the action of the lamp. In this respect, a diode operates very much like a one-way valve. One recent application is in the instrument panel of the Rover 213. Here, the diode is used to block an alternative earth path for the luggage compartment lamp through the instrument panel warning lamp. So let's look at how the circuit works and in particular the diode. Whenever the luggage compartment lid is opened, the switch in the latch mechanism closes. This lights the interior lamp by completing its circuit from the battery through the switch to earth. In addition, if the ignition is switched on, a warning lamp circuit is also completed, lighting the lamp on the instrument panel. The warning lamp circuit is from the ignition switch through the diode and the luggage compartment lid switch to earth. When the luggage compartment is closed, the switch opens and the interior lamp and warning lamp circuits are both broken. It's with the compartment closed and the ignition off that the diode functions. If the diode was not in the circuit, the interior lamp circuit would be completed by the alternative earth path through the instruments, and even with the compartment closed, both lamps would light. In the first section of this program, we saw that a car's electrical system is essentially DC, and that this is because a battery is used for starting. We also saw that the alternator which makes the car's electricity generates alternating current, and that this has to be converted to direct current before it can be used. We saw that this is done using a rectifier built into the alternator. This rectifier is simply an arrangement of diodes and relies on the ability of each diode to allow current to flow in one direction but to block the flow in the other. The Zener Diode, however, operates differently. It behaves just like the pressure relief valve in an engine lubrication system. It's used as a voltage regulator to stabilize the voltage in a circuit at a predetermined level. To do this, it's connected between the supply conductor and earth. Normally, at the predetermined circuit voltage, the Zener diode behaves just like an ordinary diode and prevents the flow of current to earth. If, however, the input voltage rises above the predetermined level, the increased current causes the diode to become conductive. By allowing the surplus current to flow to earth, the output voltage is prevented from rising. When the input voltage falls, the Zener diode switches off and once more blocks the earth path. By regulating the flow of current in this way, the output voltage is maintained at the required level. The second semiconductor device we're going to look at is the transistor. Although used extensively in modern automotive systems, they're seldom seen. They can be identified by their three terminals. These are known as the collector, the emitter, and the base. The action of the transistor is more complex than that of a diode. It's sufficient for you to know that it can be used either as an electronic switch or as an amplifier. The use of a transistor as a switch is typified in the breakerless ignition system. Here, the transistor enables the coil primary earth path to be switched electronically rather than mechanically, thereby replacing conventional contact breaker points. The transistor in the ignition amplifier unit is switched on and off by a series of pulses from the reluctor and pickup coil in the distributor. The reliability of semiconductor devices like the transistor and diode has led to numerous applications in the cars of today, and in many instances, complex arrangements are sealed away for life in what appears to be a simple plastic box. Although internally these boxes can be quite complex, you need only be familiar with their role and how they're connected in the car. Their inherent reliability has enabled troubleshooting to remain a matter of checking the electrical wiring between the battery, the box, and the other circuit components. Poor connections with their high resistance are still by far the most frequently occurring faults. At this point in the program, stop the tape and answer the series of questions in section 4 of the accompanying workbook. When you're ready, restart the tape and resume the program. In this final section of the program, we're going to look briefly at the latest automotive electronic systems. Developments in miniaturization have enabled many thousands of electronic components to be combined on a single piece of semiconductor material in the form of an integrated circuit or microchip. By eliminating the use of individual components and the corresponding mass of wiring, these microchips have not only allowed a greater degree of reliability, they've also enabled the introduction of systems that would otherwise be impracticable. Often, even these devices are just part of a more complex system. These are the electronic control units which are now fitted in most of our cars to control fuel injection, engine management, and programmed ignition systems. In this respect, the microprocessor is perhaps the most important development of integrated circuit technology and has led to a radical and new way of thinking. The microprocessor has been described as a computer on a chip. Although not strictly correct, this description is a good indication of its power. The microprocessor is in fact only one part of a computer, the processing or interpretive part. But to be of use, it must also have a means of collecting information, an input, a memory containing a program to tell it what to do with the information, and a means of outputting or acting on the results. In this respect, the Montego programmed ignition system is a computer. Here, the input to the ECU is from various devices located at strategic points around the engine, which continuously sense engine speed, crankshaft position, engine temperature and detonation. And the output is a means of switching the earth path of the ignition coil primary circuit. The microprocessor is located inside the ECU together with a memory device containing the control program and a store of ignition timing data. This data represents the ideal ignition timings for this particular engine for a range of engine speeds, load and temperature conditions. The control program in the memory instructs the microprocessor to receive information from the engine sensors and to compare it with the stored data. It also tells the microprocessor how to output the resultant information. In this case, by switching the coil primary circuit earth path. By continuously monitoring the engine running parameters in this way, the ECU controls the ignition precisely. Just one example of the ultimate in microprocessor technology and how it's been used to provide the levels of drivability and reliability demanded from the cars of today. As you can imagine, the state-of-the-art electronics contained in electronic control units are extremely complex. But although they represent circuits that would otherwise require an amount of wiring that could cause a few headaches, their solid-state construction makes them incredibly reliable. So much so that if a system fault does occur, by considering the ECU as a black box. Troubleshooting remains a matter of checking the wiring to and from the unit and its sensing devices. In this program, we've looked at electricity in detail. We first saw the need for a circuit and looked at the properties of electricity. We then looked at the simple relationship between voltage, current and resistance, and we saw how each of these properties can be measured using a multimeter. Next, we considered the various components which can be used to control the operation of a circuit in a more precise way. We first looked at the resistor and the capacitor, and then the diode and the transistor, two semiconductor devices. We saw how all of these electronic components can be miniaturized and combined in their thousands as an integrated circuit, or more recently as a microprocessor. Finally, and most important, we saw that the development of microprocessor technology has enabled the introduction of systems that would otherwise not have been possible, and although these systems are becoming more complex, by the same process, their reliability is becoming considerably enhanced. So much so that, although it's not obvious how many of these systems work, you can be sure that if a fault does occur, it's almost certain to be in the electrical wiring and Ohm's law will apply. Now you've come to the end of the program, so stop the tape and answer the series of questions in section 5 of the accompanying workbook.